So first is our derivative of sine inverse. And if you have sine inverse of x and you want to find the derivative, well then the derivative happens to be 1 over the square root of 1 minus x squared, which is like nothing like you started with. Where did the sine go? It's not there anymore. So the derivative is really weird. Because you were used to sort of like, oh, with derivative of e to the x, you get an e to the x kind of thing with power rules. There's still a power. ln x was the first hard one, right? That one was 1 over x. That looks completely different than ln x. But this one, the derivative of sine inverse, is completely different than what you started with. So, how do we prove this? Well, if you started with your regular sine x graph, and you switched x and y, this is technically sine inverse of x, right? Because sine inverse is the inverse of y equals sine x. How do you find an inverse? You switch x and y. And if you just decided not to simplify, then you would just keep it as x equals sine y. But if we have x equals sine y, we could do implicit differentiation. Do d dx of this side and d dx of the right side. And d dx of x is just 1. And d dx of sine y would be cos y dy dx. And from this moment, I'm going to give you 2 options for figuring out the proof. Okay? One will be an algebraic option, and the other one will be a diagram option. And I think because when you deal with sine and cos, what do you have to draw? A triangle. So if, and I'll do it in purple here, if I wanted to draw a triangle of x equals sine y, and I draw it in quadrant 1, that would mean the angle is y, correct? And sine is opposite over hypotenuse. This would be x, and hypotenuse would be 1. And if you did sine a squared plus b squared equals c squared, do you see that this side will be the square root of 1 minus x squared? Which, if we look in our answer to the derivative of this, is sort of like, ooh, that's kind of something in my answer. This might be important. Well, if I got my dy dx by itself, method 1 using the triangle.
Grade 12.
I have a grade 12.
If an alumni was looking to do a grade 12 survey on motivation and organizational behaviors,
could they come in here and do that?
could I give you the papers?
Yeah,
Okay.
for sure.
Okay. Thanks.
Okay. Woohoo, you get to do a survey. Yes, I love survey. Okay. But if I got dy dx is 1 over cos y, if you looked at your triangle, cos is 1 over what? Adjacent over hypotenuse. Can you see that from here, that cos of y would be adjacent over hypotenuse? The adjacent side over the hypotenuse. And then, if I use my triangle, I'm done my proof. Because I could just go 1 over, and I know that cos is 1 over x squared. Okay? I could also use algebra. And algebra would say, you know that cos squared of y is 1 minus sine squared of y. So cos of y, if you square rooted, technically would be a plus or minus there. But because of the restrictions on the domain, and because of inverse stuff, it is only the positive part. And so now we could substitute in, and we would get d dx being 1 over cos y. And 1 over cos y is square root of 1 minus sine square y. And sine of y is defined here to be x. So when you have a sine y, you could replace it with x. Me personally, I like the triangle. I think it really is easy to see, easy to create, and easy to get the answer from. The algebraic way is a little bit confusing because you have to first think of an identity, and the reason we have to think of an identity is that we can substitute back only if we have that x equals sine y. So I find the triangle actually quite helpful and quite useful for figuring this out. And so you can find any inverse trig derivative with this triangle method. So a recap of the first one. To find the inverse, we start with the regular function. We switch x and y. Switching x and y gives us our inverse function, but just in a different form. We use implicit differentiation, and then either we use the triangle to substitute back in, or we have to think of a way of taking our final answer and writing it in terms of sine only. Because we have, whenever you have sine of y, you could substitute an x. We're going to do both methods again for tan inverse. Okay, we start off with y equals tan x, and if we switched x and y, this is technically tan inverse of x, just written in a different way. So because that's tan inverse of x, if we do implicit differentiation of that, we should be able to solve. Now, using the triangle. If I use the triangle here in quadrant 1, the angle is y, and tan would equal x. Well, tan is opposite over adjacent. So in my triangle, that's where I'd label my x, and that's where I'd label my 1. A squared plus b squared equals c squared. 1 squared plus x squared equals c squared. There's your 1 plus x squared with a square root. You can see your answer is appearing already. But there's no square root in our answer. Why? Well, what's the derivative of tan? Shortcuts? Secant squared. Maybe. There it is. And secant squared, if I move it to the other side, I can write it that way, or, oh, I wanted purple. There's like, there we go. Some delay. Wait for it. Patience. Maybe if I touch the screen somewhere else, it'll be like, it'll want to do. There it is. See, it knew. That's what it wanted to do. So using your triangle, can you see from your triangle what cos of y is? Cos of y would be one over 1 plus x squared. And we have cos of y squared, so that would become squared. Which means that the derivative of tan inverse is 1 over 1 plus x squared. How would we do this if we were using the algebraic method? The algebraic method says you need to write tan of y instead of secant squared. Do we have an identity that involves secant squared and tan? Yes. Right? Secant squared is tan squared theta plus 1. So we can substitute tan squared y plus 1 in there. And since tan y is x, tan squared y will be x squared. So this one, the algebraic method, I think is actually a little bit nicer than the previous one. So the algebraic method, you need to be able to get a tan y if you're solving tan inverse. Because you can use, right, that as your substitution. We know that tan of y was equal to x, so we can substitute it in. But again, I really like the triangle method because you can just use your trig understanding of sine, cos, and tan, opposite over adjacent, to plug things in. Secant inverse. Look how crazy looking this one is. It even wrecks the projector. Oh, there we go. So again, if you started with secant x and switched x and y, this is technically secant inverse of x. Just have to believe my writing is nice. That's secant inverse of x. So again, we do implicit differentiation of this. How does the triangle work here? If my angle is y and secant y equals x, that would mean cos y equals the reciprocal, right? 1 over x. Which would mean this would be 1, this would be x. A squared plus b squared equals c squared. Can you see that this side would be x squared minus 1? Okay, not so bad. How do we do the derivative of secant? Remember the derivative of secant? It is secant tan. So you would have a secant y tan y, and then because it's implicit, you would multiply by the dy dx at the end. And if I solve for my dy dx, I would get 1 over secant y tan y. On my purple one, can you see what tan y is? Tan y would be opposite over adjacent. So if I go to my purple here, dy dx equals 1 over, well, secant y, that's x. That you get right from the beginning. Or the fact that if cos y is 1 over x, secant y is x over 1. Tan of y from your triangle is the square root of x squared minus 1. And you're done your proof. Really easy from the triangle. If you were using algebra, you would have to use the fact that secant squared and tan squared are related. So tan is the square root of secant squared y minus 1. Again, we're only using the positive because of the inverses. Technically, the algebraic, I should do some more proof. And technically, triangle-wise, I could do some more proof, right? If I assume x is bigger than 1, then secant could be either in quadrant 1 or quadrant 4. And then we have some stuff to work with in those situations. But we're going to keep it simple because it works out nice and simple if we just think about quadrant 1. As far as remembering, you will not be asked for the formal proof with all the extra details on the AP exam. But they will expect you to know what the derivatives are. You have to know these shortcuts. And you don't have to use Newton's quotient and the limit to figure these out, because that would be the next level of difficulty. So algebraically, you would then replace the secant with the x, and the fact that tan is the square root of secant squared y minus 1, well, that secant y is x, so you get the same thing. But again, I think it's easier to see from the triangles. And then we have the other three, which we're not going to prove. We have the derivative of cos inverse, which you could, again, do from your triangles. It's exactly the same idea. The derivative of cotangent inverse, and the derivative of cosecant inverse. And I'm going to go back and just talk about the notes, because the note is kind of an interesting thing. So if I draw a triangle, and you have a 90-degree here, okay? And I make this theta, and if I think in radians, does it make sense that this is 90 minus theta in degrees, or in radians would be pi over 2 minus theta? And what's interesting is that in regular math, if I call this A, B, and C, you would know that sine of theta, does it still appear if it disappears? Yes, it does. Okay. Sine of theta. That won't happen on the video. The video will nicely just take this. My projector just looks like it's losing its light bulb. Sine of theta would be opposite over hypotenuse, right? And cos of the other angle is exactly the same. Agreed? So because of that, anytime you want to find cos inverse, or, in this case, if I said cos of theta is adjacent over hypotenuse, then sine of pi over 2 minus theta is also A over C. It'll always work out that finding inverse of the angle will just be, if you found sine inverse of the angle, okay, it's the other one. So you just have to do pi over 2 minus it. Because if I found the wrong angle, I can always find the other one by doing pi over 2 minus it. So because of that, with the inverses, people remember 3 of them: sine inverse, tan inverse, and secant inverse. Because if they wanted to find the other ones, they just have to do, well, it's going to be pi over 2 minus that. And if I did the derivative of the right-hand side here, what's the derivative of pi over 2? It's just going to be 0. And if I did the derivative of negative sine inverse, well, the derivative of sine inverse was 1 over the square root of 1 minus x squared. And so now we just have a negative sign. So you'll see a connection between the cos inverse, and as far as memorizing them, this is helpful, right? Because you're sort of, if you see the connection. the derivative between cos inverse and sine inverse. And there's just the negative because of this idea in triangles. That if you found the wrong angle, you just have to do pi over 2 minus that angle to find the other one. And the same is going to be true when we do cotangent. Cotangent will be always pi over 2 minus tangent. Whatever the angle for, because tangent's opposite over adjacent, cotangent's adjacent over opposite, it finds the other one. So, oh look, it's just the tan one with a negative. And same thing happens with cosecant and secant. And so the ones that we deal with the most are the ones that are positive. And then the other one is just going to be the negative of that. So with that, let's do some questions. We can have chain rule questions with our inverse ones. Find the derivative of sine inverse of 5x squared. So here's our derivative. How do you do the chain rule? What is the outside function? The outside function is sine inverse. And now you're going to have to make sure you don't get confused with the inverse symbol as a power rule. Oh my goodness. So first we would do 1 over the square root of 1 minus, keep the inside the same. So the 5x squared stays the same. And then multiply by the derivative of the inside, which is 10x. So I'm going to take out my highlighter just to point out something. You see how that's your inside, where I highlighted in yellow. So when I say keep the inside the same, that 5x squared has to stay the same in that spot. And then we multiply by the derivative of the inside. I feel like this weekend would be a good weekend to make sure you go through and maybe even make a list of all the shortcuts that you have. Take a picture of that list so it's on your phone. Have your phone send you that list in intervals of 13 hours. So you review it every 13 hours. There will be some times in the day you will be busy. There will be some times you'll get the review and you won't be busy. So it should get yourself used to, okay, these derivative rules. And for the main ones, write out the words. Chain rule. Derivative of my outside function. Keep the inside the same. Multiply by the derivative of the inside function. Because we need to be really good at all of our shortcuts, because our take-home quizzes are probably going to be just, they're going to go up a level of difficulty pretty soon. They've been pretty, I know you don't think so, but I'm going to tell you that they've been pretty tame so far. And we're going to up them a level. Ooh, and you're like, they didn't feel tame to me. I know. And you're going to really need to know all of your derivative rules really well. So, what's our derivative of tan? Tan inverse, sorry, is 1 over x squared. So there's my inside. I'll highlight it here. There's my inside. There's my inside. You see that inside we now have e to the x. So I have a chain rule. First, I do the derivative of my outside function, keeping my inside the same. And this is hard on the computer, that's why it's going so slow. It's a lot of thinking for the computer. And then we multiply by the derivative of the inside function. It's a good thing it's a Friday, because the computer seems like it really wants to crash. You can try to work ahead on these if you'd like. I have cosecant x times by secant inverse of x. Do you see I have a product rule? Product rule says keep one the same, do the derivative of the other one, then keep the other one the same, derivative of the first one. So if I keep my cosecant the same, the derivative of secant inverse of x is 1 over x times the square root of x squared minus 1. Then I keep my secant inverse the same. And what's the derivative of cosecant? Negative cosecant cotangent. There we go. We've almost learned all of the shortcuts for derivatives that exist. Can you think of any function? Well, we haven't technically done the other log functions. Log base 3, log base 7, log base. We haven't. I put it on a review sheet for you, but we haven't formally done it. But is there any other function that you've ever used that we haven't done a derivative of yet? Something to think about. So here's the last one that we haven't done. Derivatives of logarithms. Maybe I'll stop the previous video